For this problem, the second open response, we have a student prepares 100 milliliters of a saturated solution of MgF2 by adding 0.5 grams of solid MgF2 to 100 milliliters of distilled water. So I'm just picturing, we have 100 milliliters of water. We add 5 grams of MgF2, and it's at 25 degrees Celsius, and it's stirred until no more will dissolve. Assuming that the volume of the undissolved MgF2, assume that the volume of the undissolved MgF2 is negligibly small. So we're being told that there's some undissolved MgF2 down here, but it's not contributing to the volume. And so what we have in here is some dissolved Mg2 plus and some dissolved F minus ions. The saturated solution is analyzed, and it's found that the concentration of the F minus is 2.4 times 10 to the minus 3 molar. So that's telling me that we have an equilibrium solution going on here. We have MgF2 solid is being dissolved, but it's not all dissolving. It's making Mg2 plus aqueous. Plus, to balance this, we need 2 fluoride ions aqueous. And that actually answers the first question before it was even asked. Write the chemical equation for the dissolving of the MgF2 in the water. So that's the answer to part 1. Now the next question says calculate the number of moles of MgF2. So this is moles, not molarity, that dissolved. Well, since we know that 2.4 times 10 to the minus 3 fluoride ions, molarity of fluoride ions is in there, and it's a 1 to 2 relationship, we could say that 2.4 times 10 to the minus 3 molar of fluoride ions times 2 MgF2 for every 1 fluoride, that's going to give us, oh sorry, I have that upside down, 1 MgF2 for every 2 fluoride. That would say that we would have 1.2 times 10 to the minus 3 moles of MgF2 per liter. That's molarity, moles per liter. And since we have 100 milliliters, we would multiply that by 0.0100 liters to get moles, and that would tell us that we have 1.2 times 10 to the minus 4 moles of MgF2 dissolved. So that's the answer to part 2. Okay, part 3 asks, make sure I'm still on here. Part 3 asks, determine the value of the solubility constant, the KSP, for this reaction. Well, for the reaction, the KSP would equal the product of the magnesium ions times the product of the fluoride ions squared, because from our reaction, it's a 1 and a 2 coefficient. And we don't put it over this because that's a solid. Now, we know that the fluoride concentration is 2.4 times 10 to the minus 3, that was given, and we have to square that. And the magnesium concentration, well, again, it's a 1 to 2, so we would have 1.2 times 10 to the minus 3 on the magnesium. And to show that, to show the work for that, keep moving this up a little bit, right, we would say, well, 2.4 times 10 to the minus 3 fluoride times 1 magnesium for every 2 fluoride, and that's how we get the 1.2 times 10 to the minus 3 concentration, so that equals 1.2 times 10 to the minus 3 of the magnesium. And then if we do that on the calculator, we get 1.2 times 10 to the minus 3 times 2.4 times 10 to the minus 3, and I'm going to square that. So we get 6.9 times 10 to the minus 9, and that's the KSP. Okay, so that's the answer to part 3. Now, the second part of this question, and I think I'll turn it over so that we can see it. It says, part 2, a beaker contains 500 milliliters of a solution with both calcium and barium ions are present at a concentration of 1.1 molar. So we have a beaker, and we have 0.1 molar, 0.10 I should say, of the calcium, and 0.10 molar of the barium. a student intends to separate the ions by adding 0.2 molar of sodium fluoride, 1 drop at a time. So we're going to add into this sodium fluoride 1 drop at a time, and this is 0.20 molar as well. Okay. Now, sodium fluoride will dissociate because all sodiums dissociate. So the question is, what solid is going to precipitate, because we're trying to separate out these ions by making a solid by precipitating it. And it tells us that the KSP for calcium fluoride is 3.5 times 10 to the minus 11th, and the KSP for barium fluoride is 1.8 times 10 to the minus 6. Now, the first question says, which salt will precipitate first? So let's just remind ourselves what the KSP means. If we have calcium fluoride, it's going to be in equilibrium with calcium 2 plus 2 fluoride. So the KSP for that is going to be calcium times fluoride squared. Both of these are aqueous, remember? Okay, and this is solid. If we have the barium fluoride, we have barium fluoride, solid. It's in equilibrium with barium 2 plus aqueous plus 2 fluoride aqueous. And its KSP is going to equal the barium concentration times the fluoride minus. So these equations are very similar, and we know that the calcium and the barium are both starting with 0.1 molar, and we're adding the same fluoride. So the question is, which one will precipitate first? So this is going to equal the calcium fluoride equation. KSP is 3.5 times 10 to the minus 11, and the barium fluoride KSP is 1.8 times 10 to the minus 6. Well, this is much larger. So if I plug 0.1 in for calcium and 0.1 in for barium, then the fluoride concentration I need is much lower for the lower KSP. So this one will need much lower concentration of fluoride ions to precipitate because the KSP is smaller. So calcium fluoride will precipitate first because the KSP is smaller, thus requiring less fluoride ions before precipitation begins. And that's how you would answer that one. Okay, so it's this one here will precipitate first. Okay, part 2 of this one says, calculate the minimum volume of the calculate the minimum concentration of the fluoride necessary to initiate the precipitation of that salt. And so we're going to take our equation, so our calcium 2 plus times the fluoride minus squared, and that will have to equal 3.5 times 10 to the minus 11, but we know the calcium is a 0.1 molar. So we have the fluoride squared, and then if we do that math, we're going to divide both sides by 0.1. So we'll say 3.5 times 10 to the minus 11. We're going to divide that by 0.1, and then we're going to square root that, and we get that x is equal to 1.87 times 10 to the minus 5, and that equals the concentration of fluoride ions, because that's what we put the x in for. And so the minimum concentration of fluoride necessary to initiate precipitation is this. And remember, units molarity. Then the third part says, calculate the minimum volume of the 0.2 molar sodium fluoride that must be added to the beaker to initiate the precipitation. So I need this concentration in the beaker. Okay, so remember, here's our beaker. We have, in this beaker, we had 500 milliliters of solution. And we're going to add a drop at a time of this sodium fluoride. This is a very, very small amount of fluoride. So what we want to know is how much milliliters in the drop. So what volume of my sodium fluoride in these drops that I'm putting in, what volume of this sodium fluoride, when I put it into this larger volume, will give me this concentration. I need that concentration of fluoride in this beaker to start precipitating the calcium fluoride. So if we look at that, we know that the molarity of the sodium fluoride, or the molarity of the drops that I'm putting in, times the volume of the drops that I'm putting in will get diluted in this large one to the molarity final, volume final. So the molarity of the drops that I'm putting in is 0.20. I'm going to assume that this volume is very small compared to the 500 milliliters. We'll see what happens. The volume that I'm going to drop in, okay, so drop in, equals the final molarity, 1.87 times 10 to the minus fifth, times the final volume, 500 milliliters. And if we do that math, we're going to get that the volume of the drop would have to equal 0.047 milliliters. So that would be the amount of the sodium fluoride that I would have to put in. And in terms of sig figs, I don't have to change this side over here to 500.047 because in terms of sig figs, it would round off anyways. And that would be the answer to the last question.